In Module 6, Lesson 16, we're going to explore box plots a little bit more and increase our understanding of what the data represents and how to create them. So in our opening exercise, we're looking at a table of Supreme Court Chief Justices, including the year that they were appointed and the number of years that they served. The Supreme Court is the highest court of law in the United States, and it makes decisions that affect the whole country. The Chief Justice is appointed to the court and will be a justice the rest of his or her life unless he or she resigns or becomes ill. Some people think that this gives the Chief Justice a very long time to be on the Supreme Court. The first Chief Justice was appointed in 1789. And this table shows the years in office for each of the Chief Justices of the Supreme Court as of 2013. We're going to use the table to answer some questions. First of all, which Chief Justice served the longest term and which served the shortest term? So our longest term would be 34 years with John Marshall, and our shortest term would be John Rutledge with 1 year. Next, we want to determine what the median number of years these Chief Justices have served on the Supreme Court. Now, to find the median, remember, we will have to put the data in order from least to greatest. So we'll have to spend a little bit of time. And if we just focus on the numbers themselves, our lowest value then is 1. And then 4, 5, 6, 7, 8, 9, and there are 2 9s. 11, another 11, 14, 16, 17, 19, 22, 28, and 34. There are 17 justices, so the median would fall at the 9th value, which is 11 years, counting from the top or from the bottom. The median is 11. Half of the justices served less than or equal to 11 years as chief, and half served greater than or equal to 11 years. From that, we'll need to make a box plot of the years the justices served. And then we'll describe the shape of the distribution and how the median and the interquartile range relate to the box plot. So in order to make the box plot, we're going to need to find the median of the first half of the data, which remember we call the first quartile, and we'll have to find the median of the second half of the data, which remember we call the third quartile. Okay, so we have 8 pieces of data that are less than the median. 8. And halfway between there would be between 6 and 7. That would make the first quartile 6 and 5/10. And then the third quartile would range from 11 to 34. And the third quartile would fall in between 17 and 19, which makes that value 18. So the third quartile is 18, first quartile is 6.5. Now that we have all of those 5 pieces of data, we can graph the box plot. In exercises 2 and 3, we're looking at a representation, a dot plot, about downloading songs. The broadband company timed how long it took to download 232 4-minute songs on a dial-up connection. The dot plot below shows their results. What can you observe about the download times from the dot plot? Well, first of all, they range from under 5 minutes to as much as a little more than 17 minutes to download the same number of songs. So there's quite a range between the two. Most of the data is spread between a little over 6 to a little under 15, which still makes that range and even the interquartile range rather large. There is quite a difference. Is it easy to tell whether or not 12.5 minutes is in the top quarter of the download times? So if we look at 12.5, the top quarter, it's not perfectly clear where the fourths are. So 12.5 could be right at the third quartile mark, or it could be above or below. It's a little tough to tell exactly which quarter that value ends up in. The box plot is being shown a little further down, and we're going to use the box plot to answer A and B as well. So question A, what can you observe about the download times from the box plot? Well, we can see the range again from a little over 4 to a little over 17. We can also see the interquartile range, which is the middle 50% of the data, which is between 8.5 and 12.5. Now, question B, is it easy to tell whether or not 12.5 minutes is in the top quarter of the download times? It's not easy to see because 12.5 appears to be the third quartile. So 12.5 minutes could be in both the third quartile as well as the upper fourth of the data. Remember, the upper fourth of the data is this whisker. So it's not really easy to tell which one it's in because it is very close to that. Our third quartile is very close to that value. What are the advantages of using a box plot to display a large set of data? Well, first of all, we can see very easily how the data is separated into fourths. Remember, this is our first fourth, and this is our second, and this is our third fourth, and this is our last fourth. And we can see the center of the data and how spread out it is very easily in a box plot. The disadvantages are that we lose the individual data points, which we can see in a dot plot, each individual data plot, where we cannot see it in the box plot. Molly presented the plots below to argue that using a dial-up connection would be better than using a broadband connection. She argued that the dial-up connection seems to have less variability around the median, even though the overall range seems to be about the same for the download times using broadband. What would you say? Well, hopefully you would argue that the scale on these number lines is very different. On the dial-up number line, we're ranging from 4 seconds to 18 seconds, or minutes, minutes. 4 minutes to 18 minutes. Whereas on the broadband number line, we are ranging from 1.5 seconds to 7.5 seconds. So when we're not comparing the same units, nor are we comparing the same intervals on our number line, we really cannot make a good comparison between those two box plots because they're not representing the same thing. Finally, we're going to look at data on the average rainfall for each of the 12 months of the year in St. Louis and in San Francisco. First, let's look at how many data plots are in each dot plot. So St. Louis has 12 pieces of data. San Francisco also has 12 pieces of data, one for each month, I would assume. Then we'll make a conjecture, which is an educated guess about which city has the most variability in the average monthly amount of precipitation, and how this would be reflected in the interquartile ranges for the data from both cities. So it would appear that San Francisco has the most variability since its data is spread from 0 to 4, a little over 4.5 inches per month, whereas St. Louis ranges from 2.5 to 5. So there is a bigger range for San Francisco. And we would assume that the interquartile range, which you remember is the middle 50% of the data, so we'd be looking at something right in here, seems to be a wider range as well. Based on the dot plots, what are the approximate values of the interquartile ranges of the amount of average monthly precipitation in inches for each city? And then we'll use the interquartile range to compare the cities. For St. Louis, the interquartile range is 4.205 minus 3.16, which equals 1.045. And for San Francisco, the interquartile range would be 3.945. So about the middle half of the precipitation amounts in St. Louis are within 1 inch of each other. In San Francisco, the middle half of the precipitation amounts is within about 4 inches of each other. So there is quite a bit more of a range in San Francisco. 4 inches is a big change. In an earlier lesson, the average monthly temperatures were rounded to the nearest degree Fahrenheit. Would it make sense to round the amount of precipitation to the nearest inch? Well, we could argue both ways, depending on what our data looked like. But in this particular example, rounding to the nearest inch, because there's such a big difference between the two interquartile ranges, probably doesn't matter and might make it easier for us to communicate it. We're going to use the data from exercise 4 to answer following questions. And the first one is to make a box plot of our precipitation for each city. And we can see then, with our box plots, the big difference between the variability in the two cities' precipitation. St. Louis has a much smaller variability and a much smaller interquartile range than San Francisco. If we compare the percent of months that have above 2 inches of precipitation for the two cities, we would have to say that St. Louis has 100% of the year in which they receive 2 inches or more of precipitation, whereas San Francisco has more than 50% of the year that they receive less than 2 inches of precipitation. Remember, the median is where our 50% mark is. And so if we're at 2 inches right here, that means more than 50% of the year San Francisco gets less than 2 inches of precipitation. So while the variability is quite different, what we're really saying is that in St. Louis, it rains way more frequently uh, and having more rainfall when it does rain as well. Think about the dot plots and the box plots. Which representation do you think helps you the most in understanding how the data vary? In this lesson, you reviewed what you know about box plots, the 5-number summary of the data, and the interquartile range. Box plots are very useful for comparing data sets and for working with large amounts of data. When you compare 2 or more data sets using box plots, however, you have to be sure that the scales and the units are the same.